All right. As hope everyone can hear me. It's safe and healthy, so we continue. We continue today with the. So this is all right. So maybe schematically. So there is. This is an elliptic curve, and there's a very beautiful subject of elliptic homology. And so in the previous lectures, we went around the subject kind of in one direction. We maybe went around like that. We talked about what would Chern classes be like in elliptic homology. We went around kind of the A cycle. And so today I want to talk the complementary and maybe more, well, it depends. I mean, in some sense it's more concrete, in some sense less concrete part. What would be, like, how would you see elliptic homology and kind of cell decomposition, kind of, cell or complexes, or maybe kind of point of view. Yeah, maybe not the best notation. Anyway, so to maybe let me get my notes here. And so if I so maybe the analogy, so analogy would be, let's say, analogy would be with ordinary cohomology of X with coefficient maybe in some. So we want multiplication, so that would be a ring. R would be a ring. And so this is cohomology of some complex. So there's a chain complex. This is our I chain, go to the differential, goes to +1 chain, and so forth. And each complex is an R module. Each term of this complex is an R module. In fact, usually it's written to be a free R module, but it's not so particularly important for us like this. And so in particular, i.e., a sheaf on spec R. And so that's this was to be a ring, it has a spectrum, and so an R module is right. And then further, there's also in this complex, there is a cup product, maybe less important, but still in cup product that takes Ci, we call it our cup product. Well, it takes Ci tensor product. It's R linear, so tensor product over with J goes to Ci plus J, and it satisfies the usual rule that the differential of alpha beta is the differential of alpha with beta plus minus 1 to the double power alpha differential. So this would be an unfortunate choice of notation. You can't tell my D from my alpha, or hard to tell my D from my alpha. And so it's really, so while we think of this, what was I going to say? So we take homology. It's usually it's this complex that is much more fundamental. So this chain complex, what is really where it's an element in the category in maybe DB Koch on the spectrum of R. That's much more important than individual cohomology. Okay. And so so various properties such as various properties of cohomology such as suspension. So there's a suspension isomorphism. Suspension property, what does it say? Suspension property says that that if I want the I plus first, and this is for reduced. So reduced cohomology is cohomology modulo. It's cohomology modulo the cohomology of a point. So there's a so maybe I'll write reduced of the suspension of X. That's the same as the ice cohomology of X itself. Both reduced. So that says the suspension shifts this complex by one. And so also there's various properties like Meyer-Vietoris, etc., which we'll discuss in a second. They all amount to saying that the functor, which goes from topological spaces to complexes, somehow to complexes of our modules, this functor, this goes to this is a triangulated. Is a function between triangulated categories. Where? So in triangulated category, well, the category of complexes is a prototypical example of a triangulated category in which we have a shift by one. So usually we define the shift by one. So if I want the kind of shift by one I sparse, that is the I plus first term. So this is the shift complex, shift by one. Shift complex this way. This is shift by one to the left. So from my childhood, I had a problem distinguishing from right to left, and so this is how propagated through my entire mathematical career. But I think I got this point right. No, you never know. Please correct me if I got right and left or wrong. But it's that also applies to right adjoint, left adjoint, and so forth. So I admit this among many weaknesses, this is one. And so this is, in this sense, that means since the suspension moves cohomology the opposite way, then this means the suspension should be like the shift by -1. So that's my understanding of the convention. And then in the category of complexes, we have a notion of a triangle. A triangle is something that looks like this. If I have a map from some complex A, maybe A may be slightly unfortunate choice of notation, but let's just some map F to some complex B. Then you define the cone of this map F. So this would be where we're at. This will then map to the cone of this map F, and then this will go to complex A shifted by 1. And so what would be what's this thing? It has so this object has to have right has to have what? It has to have a subcomplex B with quotient A. And so then we take then, this means we just take direct sum, or maybe I'll write it in the opposite way. Take this direct sum of the two, but with differential which is, so it has to be a 2x2 matrix, and it's since B has to be a sum complex, means in this corner here I have to have 0, because this is because B is sub, so it has to preserve B. Then here we'll take just the differential of B. Here we take the differential of A, but shifted by 1. And usual convention, normal convention, that this changes sign. If I shift something by 1, this changes sign. And then well, here I'll just put F. Okay. This is a triangle in the category of complexes is a triple that's isomorphic to triple like that. So what makes it triangle in this category. And so then right, the fact that F is a map of complexes means that this new differential that the new differential squares to 0. So exercise. And so then analogous notion. So analogous notion in topological spaces. For topological spaces, we have the cofibration sequence. In fact, this is I don't know the history of the subject so well, but I think this is first actually appeared in topology, and then Puppy meant so this is also called Puppy sequence, and that's I think he missed one of the axioms of triangular category. Well, like I said, I'm not an expert. For topological spaces, there's an analogous sequence called cofibration or sequence. And you can see it behind me, but I'm going to draw it here. So suppose I have a map. So the complication with comparing with cohomology is that cohomology is a contravariant factor. So I'm going to write a map of spaces, but then we have to, maps on cohomology is going to go the opposite way. But suppose I have a map from X. Suppose I have a map from X to some Y. Well, maybe X is like a circle, just for X. There's a map to some set Y, which maybe Y looks like that. And then this is the image f of X sitting inside Y. Then for a variety of reasons, it's good to represent this map. First thing to do is replace the target of the map up to homotopy by something that makes this f an embedding. Namely, first we take, so we can represent this map like this. We take, so maybe yellow was an unfortunate choice for the color of y, but let's continue with that. So we have we can consider the mapping cone of this f. What's the mapping cone? I take a cylinder over x, and I glue it to y along the image of a map. So this is the mapping cone of f. Mapping cylinder of f. So that so this is my y, and it's clear that this is homotopy equivalent to y itself. Right, so maybe I'll just write homotopy equivalent like that. So we just shrink. So this is, if I just shrink, take that cylinder and just shrink it here, so that will be my homotopy, and then I have my map now is replaced by just an embedding. So this is my x goes into y. And so now I've done this, I can, this is sort of equivalent to how well, anyway, to what we did above. I don't want to scroll back. And so now that we have that, we can mod out by x. We can safely collapse x. So we collapse. And so then what would happen? Then we would we collapse the image of this map x. So this means we get instead of a cylinder, we get a cone. The cone is still a cone over x, so it looks like that. And so we go, this is this cone of this map. But then with this sequence, this sequence goes on forever, because if we take, now here we can go by the same, here we have an agile map from A shifted by 1 to B shifted by 1, and so on. And similarly here, the sequence, you can continue in the same fashion forever. Here we collapsed, so we have from map from x to y, and we collapsed x. So now we have a map from something which is y, and we collapse the source of this map. So what will happen if we collapse this? The source of this map is y, and we collapse y. Then what will happen? Well, we're going to get a suspension of x, right? We took y and we collapsed it to a point. So this is why, this is where that, what that point is. This is what remains. This is what remains of y. And so then we get the suspension of x, and then we can continue. So this is one. And so we get this map, kind of the suspension. A map between spaces, natural maps between suspensions. So this is just the suspension of y, and so on forever. And so in the basic result is that if I take the sequence fundamental result about the sequence. Is that if I take the homotopy classes from, let's just, let me take maybe whatever I have, the I suspension of X, and then I take homotopy classes to whatever, to some, maybe call it Z, and then, so this is the, so since I take homotopy classes from I suspension of X goes to some Z, this is any. Then I get, so this is, so I'm taking maps from, so this, the arrows get reversed, so this is goes, so this goes from here, the homotopy classes, I suspension of Y to whatever. And then this goes to, so that, right, and then this goes to the previous term. Now this is this sequence is exact. And then moreover is exact. So this, if I take since I'm taking maps, so it's, what does it mean to have an exact sequence of set? But in fact, it's an exact sequence of, so if I take maps from, so the homotopy classes from the suspension of X. So if I take, like, you know, loop that into that, that already is a group. It's a group by the same reason as a fundamental group is a group. So because if I can take, you know, kind of two maps like that. So if I want to take a, I have a suspension. I can map it to composition of the suspensions like that. And then this mapping to Z. This will.
You could say that it is a fundamental group of the fundamental group of the mapping space from X.
Yeah, exactly right. I mean, this is what Roma is saying. This bind junction. This is a fundamental group of it. Right? Exactly. Yeah. But so this is the same kind of operation that defines a product on fundamental group. Really defines it like that. This is the product. And in fact, if I take, you know, if I take S2 and higher, this is an abelian group. I mean, whatever, S bigger or equal. So maybe this is bad notation. This is an abelian group. By the same argument as why pi2 is an abelian group. So that's the exact same argument. And so this is this sequence. If you go deep in it, this is going to be an exact sequence of abelian groups. And this is all cohomology theories are defined so that they you know, they maps to somewhere. I mean, it's just Brown representability. So every cohomology theory is going to be this is how you get long exact systems in cohomology, right? And so this is saying that to say that so the long exact sequence corresponding to the fact that this cofibration sequence gives you a long exact homology. Well, you can also say that the cohomology, ordinary cohomology, takes triangles, two triangles. Okay, so that's kind of important. Right. So this is maybe a slightly more elaborate. So how do you see? You can see a whole variety of different. So in general, the general. So there's a. So the general notion. There's a. Or maybe I say this is homotopy limits, co-limits of spaces. They go to homotopy limits. Sheaves on spec R. But I don't want to go into general categories here. I'll just give you for finitely many, for kind of finite homotopical limits. Just this all, or also infinite, but this is somehow, this in practicality, this reduces to just one notion. So suppose I have, so practicality, this is reduces the following notion. Suppose I have, instead of having one map, suppose I have two maps. Suppose I have some space X and two different maps, maybe F and G, to some space Y. So very kind of, the general notion could be reduced to this notion if X is a disjoint union of some bunch of things and Y is the disjoint union of a bunch of things, and I have two different maps, I want to kind of glue them together. And so now the space I want to consider, what would be the space I want to consider is the following. Suppose I have, so this is, if X is, still I have my Y. Let me choose a different color for Y. So this is, there is Y, and X, let's X still be a circle in my graphical representation, and then I have two different maps. So maybe one looks like this 8 I had before, and the other looks like, well, if I can draw a trefoil, I'll attempt to do this. So this is kind of F of X, and there's G of X. And what I can do is I can take a cylinder over X and glue this. So maybe try to take a space like that, where this cross section is X itself. This is my X. So I take a cylinder and I glue it here. And so what I would like this map to be kind of like the kernel. So this is the kernel of two different maps. So maybe, how do we, what was the, so this is, so maybe this is my space. Let's call this space. I already used Z for something.
More like a coconut.
Yeah, right. That's right. So this would be that's right. So this is Roma is right. So this is, let's call this space. We already had a Z, but let's call this Z now. Let's still call this space Z. This is different Z. This is different from before. Maybe before I should have called it like omega or something. So then the cohomology of Z, what would we like it to be? Exactly, exactly. That's right. That's right. So it's a co-equalizer. That's exactly right. So this cohomology of that would be sort of like, you know, what wants to be like the kernel of two different maps from. So I have a cohomology of Y, and then they have two different maps. So I can take the difference F minus G going to the cohomology of X, right? But remember, in category complex, we don't have a kernel; we have a cone. So what it really is I take a cone of this map, and I shift it by one cone of. It really is this. And I shift it, I think, by -1. So I already apologized ahead of time that I sometimes confuse left and right, but you know, you can. I'm very happy if you correct me on this sort of mistakes and other kinds of mistakes. So that's in fact kind of the most general thing I will ever need to glue spaces out. So this is used to glue spaces out of thing, and this is and so this exercise check that Maris check that Meyer Vitoris is a special case of this. Okay. We will only check the simplest case. I suppose we have a gluing, so this kind of fundamental, really kind of the simplest case of Meyer Vitoris is that we can glue. It's just like gluing of just really one cell. So if I want, what does it mean in this language to glue one cell? It means that I have if I have glue an N cell to X, this means I take as my Y, or maybe let's call glue an N cell to some space. What will be that space? So glue, we already have X and Y, so maybe some space and Z. So what are the other spaces? X, Y, Z, maybe W, since it's W. And what we're gonna be? So then we take the as X, we take the n dimensional, n minus one dimensional sphere. That's our X. Or maybe and I have a map that goes to embeds it as a boundary of n-dimensional disk, and I have some map, whatever. This is glue along an attachment map. F, so this will be attachment F to some W. And so then this result of this gluing is, well, it's the co-limit on this diagram, which means just a push out. So that's just, so this is W with the cell glued. Okay. And so this means this the fact that this is, I don't know, there's some notation for push out, but I think something like that. But just what I really mean is just this push out. Just mark it with. That's, so if you want to know what's the homology of a given space, well, if it's a homotopy equivalent to CW complex, which we always assume it is, so then you can obtain your space successfully by attaching cell at a time, and then at each time you compute a cone of some map. That's how you this means this is how you reconstruct the homology. So in a current situation, the cells, so this was there's a motivational discussion of ordinary homology. In a current situation, cells, the notion of a cell becomes more interesting. So then we have equivariant cells. Work with. So this is the notion. So what's an equivariant cell? Previously, what was point before? So previously, kind of the basis of full topology was a point, and there were different things. Or disks were just different incarnations. Disks of different dimensions were just different incarnation of the same notion of a point. So, but now point is changing the role to orbit of a group G. Because in non-coherent situation, well, point is the smallest topological space you can have. Everything else is built out of points. In a coherent situation of a group, and the smallest it can be, it can connect on an orbit, which is one single orbit is the smallest unit of a topological space you can possibly have. And so there are many of them. There's a IE, so there's a the kind of a choice of take any subgroup that's an orbit. And so then the equivariant cells have the form Dn cross some orbit, where here the group acts trivially. And here it acts as it acts. And so then we have an attachment maps are, well, equivariant maps. So the attachment maps would be that if I have Sn minus 1 cross, so that's the boundary of this. This may very well go by some map F to previously constructed space W. And then, well, this is an obvious embedding into Dn cross G mod H. And so then I have this with one cell kind of along this cell. And so this is my This is my push out here. Means its cohomology is then some cone of things I already know. So that right. And then this is one part, is that the cells are equivariant, and also we have to say what's the equivariant cohomology of each individual piece. So that's the equivariant cohomology. So if I wanna, so this is right. So this is and now cohomology of each individual cell. Well, by cohomology should be homotopy invariant, so this is just as well as some graded in principle something. So this cohomology G mod H, and that should be some specified sheaf. And we need an ingredient. So previously we used just cohomology of a point, but now I have to use cohomology of that specified sheaf on what? On the cohomology. Should have chosen on the spectrum. Cohomology of maybe all right. So there was some G covariant. I should have chosen a shorter word, right, to copy cohomology of G mod H. But by basic kind of axioms of what we expect from group actions. So remember, we expect that if I have a space with a free group action, then its equivariant cohomology is just the cohomology of the quotient. So that's kind of the basic axiom we expect. So this just comes. This is the image of the structure sheaf. So the ring itself is called the structure sheaf under. So the theory should be under. So the theory should be. So if we take cohomology, it's a contravariant theory with respect to covariant maps. When we take the spectra of cohomology, it'll be covariant with respect to covariant maps. So that we have to have a map spec of our cohomology. I'll just abbreviate. H equivariant cohomology of a point should map to the spec of G equivariant cohomology. So this is maybe to reiterate. So if I make covariant cohomology, then I have to have maybe an interesting ring or an interesting maybe say ring or some other space which remembers the group equivariant cohomology of a point. Then if I have a group homomorphism that should induce a map like that, and then the equivariant cohomology of a general space, I can decompose a general space, well, not a general space, what people call reasonable space or something. That is something which is homotopy equivalent to CW complex. Let's say I can decompose it in cells, and each cell in each cell, if I argue one cell at a time, it just means that at every step I have to compute a cone of some map. That's how you compute the cohomology. And so now in elliptic cohomology now, in a current we don't have rings which have this, we just have spaces. Have schemes. Well, schemes which are take this place. Just you take the whole the spec of that. Don't have, so we don't need, there's no need for them to be affine. If we state it like this, you're just taking, we're computing with sheaves on some scheme, and there's no need for this scheme to be affine, right? We computed it. If you think of the ordinary cohomology being cohomology of some complex or whatever, there's in principle no need for a complex to be a complex of modules over some ring. It could be a complex of sheaves on some arbitrary scheme. So this is the principle. For the definition of cohomology, there's no need to assume that your base scheme, you're working over some affine scheme. There's just no need for that. You have these schemes. So and what are they? I remind you. So this is the so abstractly maybe. Abstractly, there's something like G bundles. They're like G bundles on the dual elliptic curve. The dual here is because I want the kind of GL1 bundles. The bundles of degree 0, they're semi-stable of degree 0. So then GL1 bundle on an elliptic curve, that's of degree 0. That's, well, this is bundles degree 0. Sorry, this takes longer to write this. So that's just this pick 0 of GL1 bundle is the same as line bundle. So on each check, that will be the curve itself. And so if the group, and so here I ask you for forgiveness now and for forgiveness in the future. I use the same letters to represent compact groups or complex reductive groups. Otherwise, it just gets very, very confusing because we will have some torus action, which is an algebraic torus, and I would like to define something in the elliptic homology with respect to that torus action. Of course, we take a compact form of that torus, but it's if we have different notation for the torus in its compact form, that will be I think that will be a nightmare. I think it's easier to remember that in topology we deal with compact groups, but in algebraic geometry we deal with reductive groups, and there's for every but this correspondence gets complicated if your group's not connected. We're not going to worry about that. If you're disconnected non-abelian group, then it gets a little complicated. We're not interested in that. We're interested in fact, we're interested in a torus and its subgroups, for which there's a natural reductive group. Depends what you mean by reductive group. So natural group scheme over integers. Let's put it like that, which is reductive at a generic point. So this is but concretely. So if G is a compact group for connected G, this elliptic homology G of a point, that's just you take elliptic curve, but you tensor it with the co-character lattice of your group G, and you mod out by the Weyl group. That's concrete. Even more concretely, we will be mainly interested in billion groups T, then equivalent elliptic homology of T or point. That's just E tensor the co-character lattice. And if I have a map between tori, one here, torus 1 maps to some other torus 2, induces, so they have this induces map on co-character lattices, and so then induces. Like for instance, so suppose if I have, suppose if I have a torus and I just take the square and I take the product. For a abelian group, product is a group homomorphism. Is a homomorphism for abelian groups. And what would be this? What would be this? This induces addition on just induces whatever group law. So for abelian groups, this is a group. This is an abelian variety. Right? So for this is just some number of copy of elliptic curve, and that's just this abelian variety. And this is directly related. Think about it, directly related to the fact that in the story in lyrical section, kind of classical story, there's you get group law from things like tensor product of line bundles. Tensor product of line bundles have to do with operations like that for one-dimensional groups. Anyway, maybe let's. Okay, so that says that for abelian groups, I have a particularly and then we have a more general homomorphism. Well, let's just if I have maybe so if I have general, I have some homomorphism, some exact sequence, some torus goes to some subtorus prime goes to 1, and then here the kernel of homomorphisms of tori. This is usually called a quasi-torus, I think. in particular, it don't have to be connected. So there's a kernel of that. This induces the fact that then if I take elliptic, maybe take this kernel gamma. So then this says then I have an induced exact sequence of elliptic homology of a point, because this is a map of abelian varieties, and maybe my abelian variety will written be additively, and then there's a kernel of that. That would be that group. Like for instance, if I have if my torus is just multiplexing group of a field, let's write C star or GM of my field. Well, okay, we're doing topology, so let's just not. We don't do algebraic. We don't do motifs at the moment, so let's just do that. And so then I have a map. C star goes to kind of Z to the N map, because the nth power, that map is surjective, and its kernel is the group of nth roots of unity. Here, maybe denoted mu n. This is just notation. And then this says that the elliptic homology would be that. So we decided that this is the group operation on the torus induces the group operation on elliptic homology. So that would be E. This is raising to the power n, which is multiplication by n. And then E, this map is surjective, and its kernel, this is denoted like this. These are groups. These are points of order on E. And in general, so over C, there's this would be n square disjoint point. Corresponding to so if I have a point of order n, this would be my fundamental. What would that look like? So I have my fundamental parallelogram, B1 and tau, and then points of order. Let me try to draw points of order 4. So that would be like something like that. Right, so this will be this is 16 points of order 4. But over some other field may look very different. Could be n points. So maybe of a point over a field of characteristic P could be P point of fatness P. It's clear that this has to be a bunch of fat points, because if I take the addition
is for n equals p.
Right. Thank you, Roman. You're being super helpful today. So maybe right. or could be, or could be 1 point of thickness of fatness p square. So this is so this is it's clear that it has to be some fatness, because if you just look at the addition law, so we kind of but to look at the addition law, then the linear term in the addition law is the usual addition. So if you add a point to itself p times, you're going to get 0. So the map that is raising to the pth power, that map has differential 0 at point 0. So the 0 is a point of thickness p. And so what point is, I think, at least c p. And so these guys are called super singular. And these are curves. And this is the locus. So this is the locus where the elliptic homology is really different from K-theory, because in K-theory, so this is I mean, you can imagine that elliptic homology is like K-theory. K-theory says we have this we have this point of view that we for us the elliptic curve is like C star mod q to the z, or you can also do the same kind of theoretically, but it is just really, so this is multiplicative group, or more generally the multiplicative group of the field. So you don't need star here. Reduced to mod some power by z. But and so this is saying, so if you think about what we'll do this homology theory, it'll be saying like I take the K theory and I kind of make it periodic with Q, and this is you can imagine all this phenomena pretty well until you get to the point to super singular curves. So because that is not, none of the curves of this type is super singular. So that's where the place. So this is I don't want to. I think speaking for myself, I kind of came to appreciate that that elliptic homology has to be a little bit complicated. I mean, it can be because there are these issues. If you want a theory that is well, anyway, that's a long story. You can, but all I'm saying is that this is. So let me get back on track of what I was trying to say. I was trying to say that we know, especially for abelian groups, we know exactly. So this is a general abelian group is a subgroup of some torus, and so this is we know exactly what are the corresponding elliptic homology of a point, and so then means we can if I have any space of which abelian group acts or compact connected group acts, then we can just cell by cell compute what the elliptic homology is. And so let's do an example. So we'll just an example would be finally an example. Let's take the let's take just kind of a figured example. C star acting on first is CP1. So we did the cohomology of a general projective space, but let's take P1. So P1 looks like this, has the south pole, call it 0, has the north pole called infinity, and then it has this rotation action. Right? And so this we can decompose out of the following cells. We can take, well, a fixed point at infinity and fixed point at 0, and we can take, oh, let me, since when you write cells, it's important, when you write actual cells, it's important to remember the difference between the compact and algebraic group. So I apologize, let me just get the U1. And then another cell is, well, you just take a cylinder, which is U1 cross, so that's my equivariant cell. That's U1. This is my U1 free orbit cross disk 1. And this is, and while we're at it, these 2 points here, that's a 0-dimensional sphere. So we're gluing, in other words, we're gluing, if we're doing non-equivariantly, we'd be gluing a segment, would be gluing a disk to, would be gluing a disk to the to the boundary of sphere. So it'll be just a segment. But equivariantly, this would be something interesting, and this is in fact this is exactly. So this is, if I may go back. Let me undo this. So this is exactly the situation which situation? Let me go back. It's just this situation. So it's this picture. It's exactly the situation. Maybe paste it here. Maybe I'll make it a little smaller. With what? So with this being, this is my CP1. And then X is just a free orbit. So X is just U1 cross. So X is. So this is a free. X is U1. We took a cylinder over U1 here, right? We get exactly a cylinder, and Y here are the 2 points. And 2 maps are the map, and the 2 different maps is I collapse the I send my X, I collapse this U1 to one port or the other point. So okay, so that means that so that what would be so elliptic homology. So maybe since I have to draw the have to let me move these points around so that we can draw the diagrams the way they're supposed to go. So Y goes this way, homology goes this way, Y goes this way. And so what's elliptic homology of Y? Elliptic homology of Y are just 2 copies of elliptic homology of a point. So this is just to take. Sorry, let me take O, 2 copies of elliptic homology, U1 elliptic homology of a point. And that's just my elliptic curve. Right? And then here I have 1 copy Well, I don't need a copy here. So you take one copy of structure sheaf of elliptic homology of now. So this means that this point. So we need to remember we need the stabilizer subgroup. So we have a point. It means two orbits of the form U1 over U1. And this U1 is U1 over the identity group. So this corresponds to a free orbit. So well, let me write it still here. So that's the U1 of U1. This is, like I said, the stabilizer here is the identity group. So this would be elliptic homology of the trivial subgroup of a point. And then how that's just that is just the structure sheaf. So this object, so what corresponds to a map of a trivial subgroup to, maybe I'll take this explanation and I'll write the, so I'll write the answer and then I'll write the explanation. Here we had, for Y, we had two copies. Not sure what's happening. So we had two copies of the structure sheaf of E, because that is the, because E is the elliptic homology of U1 over point, and the point is what we had here. So we have two copies, and here I'm going to get just one copy of the structure sheaf at the origin, right? And this will map this way because it's a pullback map. And why am I going to get this? It's because I'm going to get it. So this is the image. This is the, because 0 is the 0 inside. 0 is a set inside E is the elliptic homology of a trivial group of a point sitting inside the elliptic homology of U1 of a point. Okay. And now what are these maps? Here I have function. These are functions, and this is just value at 0. And so then I have, so maybe, so here I have two functions, an element in here, or kind of two functions, f1 and f2, or maybe just not, let's not confuse them with, we call them g1, g2. Oh no, this confused with the group. So how about phi1, phi2? And then, so here, what would be what's the map that this, so if I glue one side of the cylinder to a point, then the map is going to be, one of the map is going to be evaluate phi1 at 0, and another map is evaluate phi2 at 0. So that's the map. And now I have to compute the kernel of this map. That is to say, the cone shifted by 1, but in this particular instance, this map is surjective. Right? This goes to 0. And the kernel of that is what? The functions. The functions. Pairs of functions. Functions that take the same value at 0, such that f1 of 0 is f2 of 0. So this is what is that? So when I have two functions and I require them to take the same value at a point, means I take two copies. Spec of that is, so if I take specs, take spectrum, what I'm going to get here? Here I'm going to get a point. Here I'm get two copies of elliptic curve. And here I'm going to get these two copies glued at a point. So here I evaluate this kind of, I have two maps from this point. So I have two different maps from this point. I can embed it here and I can embed it there. And then here, this means they're now glued here. In other words, this is the picture. So this is what we computed. So this is what we have computed. With churn classes. And this exact sequence, this is the normalization. So this is, you take functions. So we take functions. What the exact sequence we got is we took functions on, or I'll just write functions O of elliptic U1 of P1. So these are functions on this, on the union of two lines at two elliptic curves at a point. Then this map here, this is the normalization. Right? So then we take, so if I have a function on the union of two lines, I can pull it back to normalization. So this is U over the normalization. So if I have functions on the union of two lines at the point, I have a function on one line, a function on another line, I have to agree. So first I have a map to normalization, and then I take the O, well, the intersect at the point. So O of the intersection. And in this case, it's surjective. That makes sense? You can continue. So this is, you want to continue like that. So if I want to do the same, for, let's say CP2, what's it going to be? For CP2, we have three kinds of orbits. So we have, maybe I'll draw a toric diagram of CP2. This looks like that. And so there's a free, again, there is one free orbit. Orbit one. There are three orbits of the form. So maybe, so this would be, what's my torus? Free, maybe I didn't say, did it say, well, what would be the torus I'd like to take? So this is maybe, maybe with the action. So let's say, so that I don't have to redo it. Let's take a torus with X with a free orbit. So maybe I'll take something like this, 8283. I don't. So then it's really the free orbit. 3 orbits which are of the, so this is my torus A. 3 orbits of the form A over A, 3 points, and then 3 orbits of the form A modulo one-dimensional subtorus. So when we computed, when we computed we compute the spectrum with return class, we computed the spectrum of, well, sorry, we don't need the spectrum here, I apologize. We computed the elliptic homology, A-current elliptic homology of CP2. Well, we computed that it looks like a union of 3 planes like this that intersect. So this is that's what it looks like. It's a 3 planes that intersect like coordinate planes in a 3 space. And then this we can there's a normalization map. We can take these planes apart.
So each plane represents a copy of E squared, right?
Right. So this is exactly. So these are E2s glued like this. Okay. So we can take them apart. So there will be 3 E2s, which is each E2 is elliptic homology A-current of a point. So this corresponds to the, this kind of corresponds to the red point. These are points. These are fixed points. Then, so if I have a function, on this, well, it has to come with a function. So a function on this union, I can pull back to the disjoint union. So a function here comes from a function there, but then it has to satisfy a condition on the intersection. So maybe there's a conditions glued along each correspond to elliptic homology of A mod one subtorus, maybe call it whatever. AI, there are 3 different subtori. This AI current homology of a point. But then so this is if I want to functions on this on 3 functions on 3 coordinate planes, they're the functions on each that satisfy gluing conditions on the so maybe I'll draw pullback of functions. Functions go this way. So pullback of functions, they go this way, and then the next step, what you get is you have to get things that glue along the one-dimensional thing. So they have they go here. But that map here, that is a not surjective map. That has itself a co-kernel, and that co-kernel is, maybe I'll put it in black. Co-kernel of this map corresponds to just a point, and that point is the elliptic homology of the trivial group. So notice there's kind of an inversion goes on. So if I have in general elliptic homology, you get something of the size which is not the size of the orbit, rather the size of the stabilizer. So here the orbits were came in three different shapes. There was one big orbit, three smaller orbits, and three very small orbits. But then we take the homology, we look at the lattice not of this orbit, but the lattice of not how these orbits are big or small, but what are the stabilizers. And so the points are the biggest. So maybe I should have. So these are, what is a point is very big. What's a free orbit is very small. So free orbit here. So this is where the free orbit sits. Orbit, and this is where the points sit. These are fixed points. I already wrote the fixed point. Okay. So in another way is that if I wanna do this cell this depicts here a cell decomposition. So that means I have an actual cell of the form. So this one free orbit is actual disk, which is depicted here. Is disk 2 cross maybe I'll write S1 squared. These are orbits of the form, the disk which is depicted, which is disk not this is supposed to be a cross S1, and then you take sorry, this belongs here. Okay, so this is, if I take that cell decomposition, you can easily convince yourself that I'm going to get normalization exact sequence for this object. And then I apologize, I want to finish with something with a different point of view on the same example. So this is because next time I want to start with actual stable envelopes, and so let me go a little bit over time, and since I'm always guilty of that, so let me do it again one more time. Is that a different point of view on the same computation? On the so when we glued CP1 out of cells, instead of gluing it like we did, we could have taken a disk, not be a cell, be just this is still gluing. So we can take a disk with its defining action and take the boundary of that disk. So there is U1 in the boundary here. And glue is just a point. So maybe this is 0.0, and this is point which is infinity, right? So another way, we could have considered the diagram. So this is what? This is like the disk bundle. This is the disk bundle in the normal space to 0. So we could take this free orbit U1 and we glue it to again this disk bundle. It also is a B of kind of defining representation. All right, in the defining representation. Maybe call that defining representation A. We get AX by A. So there's an element here called A. And so you take the kind of disk bundle in this defining representation A, and then we take the push out with respect to this point, and that this push out is CP1. And so then you can view it that same push out. You can, this is essentially the same computation, but in this computation we made the roles of 0 and infinity slightly asymmetric. This means in this computation you can write it as you take elliptic homology of CP1, maybe O, take O of elliptic homology, my equivalent elliptic homology of CP1. I can restrict it. I can consider what would be the restriction to infinity. The homology A to just the point infinity. And so in this diagram, I can just somehow concentrate on this part. And then what would be the kernel? The kernel would be the Tom sheaf of the defining representation, so to speak, over kind of 0. This is kind of a vector bundle. Right? And so correspondingly, I'm gonna take the same. I take functions on a union, but instead of pulling back them to both of the slides, I just pull back to one. So I restrict. So maybe let me draw it in 2 different colors. So functions here. Here on here, I'm going to pull back to functions on. So this is maybe corresponds to the fixed point infinity, and this corresponds to the fixed point 0. I just pull it back to one line. So this would be a surjective map, and the kernel of that is, well, we know how to think about Tom sheaves. That are the functions on this line that vanish at the point. Right? So this is you you consider, you take all functions on this union of 2 lines at the point, well, 2 elliptic curves at the point, then you get, so in other words, you kind of you get this structure sheaf. What's that guy? There's just structure sheaf of this elliptic curve that corresponds to this fixed point. In that object, this object here, this is the ideal of 0 in the structure sheaf, right? So if I think about functions on a union, I can think of this as a functions on one side, and then to glue this, the kernel of this map are the functions on the other side which vanish at the point. And I think I've exhausted the possibility to explain this as any kind of. And so what would be the analogous for general n? So if I have my CPN, so maybe this is my picture of CPN. Inside of it, I have CPN minus 1. And here I have some point, maybe we call it 0, and that point has the weights of the normal bundle are, maybe I'll write them kind of AI over A0. These are the weights of the normal bundle. We can, and so then if I take if I take this cell decomposition, means I want to glue CPN and the Thom space of this normal bundle. So in other words, I take then what I get is that I take elliptic homology CPN. Sorry, the structure sheaf of elliptic homology of CPN that subjects to the structure sheaf of elliptic homology of CPN minus 1, and the kernel, well as the Thom sheaf for this weight AI over A0. Maybe I'll just for this. This is a particular for representations. Maybe A1 over A0. So forth AN over A0. And so if I look at the spectra, what would that look like? So if I take my that union of planes, so maybe I'll draw it slightly differently. So if I take that union of planes here, and then one of them I single out, there's this part that corresponds to, this corresponds to 0. And I can take functions and I restrict it to just the part to just this part. So I take a function that restrict here, and the kernel, what would be the kernel? The kernel is well, this is what always happens when the yeah, this means the computer is tired to doesn't want to work anymore. So just write the kernel by so the kernel are the functions here that vanish. It's the ideal. This is the ideal. That space from an analysis of Thom space, that is the ideal of this green part here. So if I take that, makes sense. So that's a. So this is you can decompose. In other words, you can when you glue coherent cells, you can decompose. You can choose different strategies. You can glue things like we did before and get like a normalization sequence. But you can also do things like like this sequence, and that would be, this would be our strategy, would be more like this. So our strategy, this would be, so this would be our strategy to construct. So so I hope this works. That this will be our strategy. Will 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 help, will make you think about this example, and you know, make sure you're comfortable with what's going on in this particular example. So that's sorry, I'm over time as usual, so I'll stop here, and we'll be happy to take questions. Any questions? Many thanks to Roma today. He's been very helpful, pointing out many, well, some of the many inaccuracies that I've perpetrated. Well, if there's no question, then I wish everybody all the best, and I see you and I'll see you next week.